third presentation of the ARMA, the Toronto ARMA Student Chapter presentation series in conjunction with NSERC-Energi Simulation Industrial Research Chair Program in Fundamental Rock Physics and Rock Mechanics. So today our presenter will be Professor Sebastian Goodfellow, and he'll be presenting about doing more with the ATV data we have, understanding stress in deep mines. So before we start, I'll like to let everyone know that we'll be recording this session. And at the end of the session, we'll be doing a Q&A. Feel free to use the chat to ask any questions if you like, anytime during your presentation, and we'll get to them towards the end. So yeah, so before we start, I'll introduce what our ARMA is, the American Rock Mechanics Association. So this ARMA was established in 1995 from the U.S. National Committee for Rock Mechanics, National Sciences, with the mission to be the worldwide recognized representation of multidisciplinary rock mechanics advancements and applications to serve its members and the public. Currently, there are 1,200 members with 40% petroleum, 35% civil, 5% mining, and 30% student membership. And there are also 14 student chapters that are around internationally. And among these chapters is currently the newly established ARMA UToronto Student Chapter, of which is hosting this session today, which is us. So our team consists of the people you see on the screen. The executive team for this chapter came together by students who are motivated to bring awareness and spread knowledge in rock mechanics in all its fields that span from geosciences to hydraulic fracturing. And I'll introduce the executive team. So we have Ali Abdelaziz, who's the president, Maylee, the vice president, myself, who is the treasurer, and Kareem Aboyana, who's a secretary, and Bezoit, who's the events coordinator. And I'd also like to thank especially Phyllis Wu, who has been helping us out in preparation for these meetings. That being said, the executive team is always looking for members and interested individuals who are willing to share their ideas and visions to promote this chapter. So we would also take this opportunity to ask the University of Toronto students intending, if they're interested in being part of the executive committee, to reach out to any of us who are shown here. So we hold these visions as we try to bring together the rock mechanics community within the University of Toronto, as well as universities in Canada and around the globe. So our vision is to provide networking opportunities with leading industry and academic professionals, provide online, offline professional presentations to our members and to interested people, provide a place where students can share and collaborate on their work through a series of open discussions, as well as share and exchange ideas and information between rock mechanics practitioners. You can follow us with the following links. So we have our website. You can register, become a member through the link in the here. And also you can follow us with our Twitter handle, which is at ARMA_UToronto. And there you could follow us to keep up to date with our upcoming events. So with that, I would like to introduce Dr. Sebastian Goodfellow, who has recently joined the Department of Civil and Mineral Engineering at the University of Toronto as an assistant professor. Before joining the University of Toronto, Dr. Goodfellow has worked for 4 years at a mining technology startup called Geosystems and led the development of a machine learning product designed to provide geological and geotechnical core logging assistance to geologists and engineers. The technology has won several awards, which is the 2019 Victorian Premier's Design Award and the 2019 Good Design Award, 2017 Disrupt Mining winner, and has resulted in government funding and capital investment. Dr. Goodfellow's focus is on the application of new technologies to conventional data sources to tackle challenges in the mining industry and studying the interactions between humans and these technologies in high-stakes mining environments to support successful integrations. And with that, I'd like to welcome Dr. Sebastian to present his presentation today.
Okay, can everyone see the screen? Yeah.
Yes.
Okay, so I just want to make a few acknowledgements. So this work was done while I was an employee at Core Geosystems. DGI Geoscience is a borehole logging company out of Toronto, and they acquired all the data for this project. Glencore Sudbury was our mine collaborator, so all the data was acquired in the Nickel Rim and Onaping mines in Sudbury, and we worked with the ground control team there led by Brad Simser. And the project was also funded by SEMI, which is the Center for Excellence in Mining Innovation, and the Ultra Deep Mining Network, both out of Sudbury. So for this presentation, we'll talk about what is this challenge we're trying to solve. We're trying to solve it with ATV data. What is ATV data? What kind of special opportunities are aligning at this moment that allow kind of this to be possible? What have we done so far, and where are we going next? So the challenge, stress state information is a critical component of both mine design and ground control. On the mine design side, there are many inputs to numerical models, but stress is a very important one. And you could imagine that the mine that you ended up designing will be very different depending on what the stress state is. On the ground control side, these are images of rock burst events. So there's sudden and violent collapse of mine infrastructure. And the ground control team is always monitoring available data. This could be microseismic data, extensometer data, making observations and referencing back to the numerical models and trying to avoid these events if possible. And a solid understanding of stress is important for managing these risks to workers in the mine. And stress is traditionally a very challenging property to measure for a few reasons. One is that it can be highly variable across a volume of interest. So, you might have a far field stress that is compressing a volume of rock, but there are many things that can affect the stress. This could be geological structures, mine infrastructure, contrast in rock type. And so all of this makes it hard to quantify the variability with point measurements. And a lot of the available methods can have high levels of uncertainty. As I mentioned, they can be sparse, and they can have low levels of success, be time consuming and financially expensive. So probably the standard method is overcoring, which from my experience forms the basis for most understanding of stress in mines that I've worked with. Another method is the acoustic emission Kaiser effect method. There are two groups out of Australia that do this. And basically what they do is they take a core sample out of the borehole and they drill, I think, 6 smaller boreholes at different orientations out of that core. And then they do uniaxial compression experiments on each of those small cores. And they measure the cumulative acoustic emission hit rate. And for each orientation, they extract the uniaxial stress where the AE starts to increase more rapidly. And then they put this into an inversion to extract the stress state. I've seen it used at a couple of mines in Sudbury. One of the big challenges with it is that, as you can see from this plot, it's not entirely obvious where the acoustic emission hit rate is really taking off. And so there's some uncertainty in when picking that value. Mini hydrofrac is another method. And then ESG Solutions out of Kingston, I believe they have a method to infer stress from the microseismic moment tensor. And so this is data from the Underground Research Lab. This was a test site for the storage of Canada's waste uranium in a Canadian shale in Manitoba. And it was kind of like this really cool underground research lab. And they were working in a fairly small volume of rock, and they were trying to quantify stress. And so this is showing the stresses from 100 overcoring measurements in a relatively small space. And so you can see that there's quite a lot of variability in both the orientations and the magnitudes. And so you could imagine that if you were just picking, one overcoring method to characterize a stress state in your mind, how there might be quite a lot of bias in that measurement. And so this is one of the challenges that we're trying to address. We're trying to address it with ATV data. So I'll talk a bit about what that is. So ATV data is a type of wireline logging technology. Wireline logging, this is a setup for that. So here you can see the steel casing at the top of the borehole. Usually there's a tripod and there's a winch in the truck. And basically this cable is supporting a probe, which is slowly being lowered down the borehole. The cable not only is supporting the probe, but it is also providing power to the probe and relaying data from the probe back into a laptop that's located in this truck. Wireline logging is used in the mining industry during exploration, geotechnical logging for mining, as well as in the oil and gas industry. Common physical properties that probes are designed to measure would be resistivity, magnetic susceptibility, gamma radiation, density, and sonic velocity. And there are two types of probes called televiewer probes. So there is an acoustic televiewer and there is an optical televiewer. And these are images of both of those. And the type of data that they create is shown on the right. So the first two images where it says amplitude 1 and amplitude 2, those are from the acoustic televiewer. And then optical on the right, that's from the optical sensor. So the optical probe can work in a wet or a dry borehole. And you can see there's little LED lights there that would light up the inside of the borehole. And then you basically just have a rotating camera taking a panoramic image inside the borehole. The acoustic televiewer is using an ultrasonic pulse to image the borehole wall. And so it needs the borehole to be fluid filled. And on the right-hand side, you can see from the optical, you've seen this vein structure, some fractures, and you can look at it in an unwrapped or wrapped view. And the wrapped view is basically just looks like a piece of core. So this would be the mirror image of the core that you extracted from the hole. For the acoustic televiewer, what it does is it obtains a high resolution oriented acoustic image of the borehole wall and does this by transmitting an ultrasonic pulse, which travels through the fluid, reflects off of the borehole wall, and then that full reflected waveform is recorded by the sensor. This little hole here at the bottom of the probe, that's where the ultrasonic pulse comes out of. And, that's where the ultrasonic pulse is recorded. And this rotates 360 degrees at each depth increment. And so the two features that we generally extract from the raw waveform data is the travel time. So that's how long did it take for this wave to travel through the fluid, reflect off the wall, and come back. And then the amplitude, the maximum amplitude of the reflected wave. And what happens here is that some of the energy from the incident wave is transmitted through the rock and some of it is reflected. And so if we had a broken out zone of the borehole or maybe an open fracture or fault, this would result in a longer travel time, right? It would take longer for that wave to travel through the fluid and back to the sensor. And as well, we now have this kind of broken out area around the borehole, which is absorbing and scattering ultrasonic energy, which is resulting in a smaller amplitude of the reflected wave. So these are the two ways that we can image these features on the borehole wall. And so this is an image showing an open fracture, both in the travel time view and the amplitude view. The more bright yellow areas are longer travel times. And then the darker purple areas are smaller reflected amplitudes. So this open fracture is, the signal is traveling into it, taking a longer time to reflect back. And as well, it is absorbing more energy through different mechanisms of attenuation. So we can view this data in two views. There's the unwrapped view. And so you'll see this a lot in the presentation. And so the y-axis is kind of the depth axis. So the top of the borehole is at the top left corner. The bottom of the borehole is at the bottom left corner. And then the x-axis is kind of the circumferential angle, right? So essentially top left corner is 0 degrees and the top right corner is 360 degrees. And you can look at it in a wrapped view as well. So that's what the raw data looks like in terms of travel time and amplitude. And what happens is this raw data goes to the company like DJI, and DJI has a bunch of data analysts who will actually extract features manually from these images. So one of the features they extract is the borehole breakout. So this is done by drawing a rectangle basically around these breakout features. So rectangle will have a distance down hole, it'll have an angle, it'll have a length, and it'll have a width. And this is image here is just showing what a breakout would actually look like. And what we see is that these breakouts are typically symmetric, and they are occurring at 90 degrees to the maximum horizontal stress in the plane perpendicular to the borehole. So it tells us something about, you know, the stress relative to that borehole coordinate system. We can look at the breakouts as a bar chart. So here I'm showing how many breakouts per meter are we seeing as we move down the borehole, or as an orientation, right? So maybe the trend of this borehole is changing as we move, the trend of this breakout is changing as we move downhole. And then we can also look at the summary plots. So this is an angular histogram of breakout orientations. Another feature is geotechnical structure, so fractures, bedding, joints, and faults. When a plane intersects a cylinder and you unwrap that cylinder, it's kind of expressed as a sinusoid. And so what the analysts will do using a software called WellCAD is they'll just fit manually these sine waves to the breakout features. Because the borehole or the acoustic telemetry image is oriented, they can get out the true azimuth and dip and aperture of all of these structures. And we can look at them in a summary view over the length of the borehole. So maybe I'm looking for areas where there are lots of fractures or not so many fractures. And we can also look at like a polar or Schmidt plot to see if there's any kind of dominant trends across the data set. Another feature is the borehole geometry. So we're measuring the travel time of this wave, and the top of the borehole is often cased with a steel tube, and we know the inner diameter of that steel tube. So we can do a calibration there and calculate the velocity of the fluid, the velocity of a sound in the fluid, and then we can use that together with the travel time for the rest of the borehole to extract the borehole diameter. And it's kind of like a pseudo caliper that you get in addition to maybe running like a 3-arm caliper. And this is useful because we can see, you know, we would expect the borehole to be, you know, we know the diameter that it should be because we know the diameter of the bit we're using. But sometimes you might see anomalous areas like this, where there's a massive broken out zone. Something like that might be of interest to the ground control team. Reflectivity is basically at every depth point, they just take the average of all of the amplitudes around all 360 degrees, all those measurements. And basically like a competent rock would be like the brownish colors, a broken rock would be the purple colors. And again, we can use this to look for areas where the borehole is significantly broken out and is absorbing a lot of that ultrasonic energy that the sensor is transmitting towards it. And lastly, there's just the survey data. So all these probes are measuring the tilt and the azimuth of the borehole. Azimuth is relative to magnetic north, and this can be problematic, you know, if the deposit is highly magnetic. So we typically don't use the trend data that's collected on the ATV. Typically, we'll use the gyro data that's collected by the mine. And so why are these companies collecting ATV data today? Well, one of the reasons is they want to validate the fracture orientations that they get out of their geotechnical logging. core logging using oriented core. So there's a method to orient core so we can understand what the orientation of this core sample was when it was in the ground. And these kind of red strike lines indicate some kind of known orientation. The challenge is that this method can have some error. So let's say the core snaps off and it's spinning in the barrel, or there's some kind of human error when they're putting this line on it. Oftentimes, the mining companies will want to validate these orientations that they're getting out of their core logging. So they'll log some holes with ATV because it is oriented to do that validation. And another reason is that sometimes the core recovery is very poor. And so this is a real example of an optical and acoustic image and the associated core box that goes along with this. And because of how highly fractured it was, the recovery was very poor. And it's very hard to understand anything about the structure or breakout orientations in this zone. But you can see that the borehole wall is still relatively intact, and we can extract orientations of these different fractures. So it's helpful in that sense as well. So what's the special opportunity that's available right now? So there's a few major trends in data collection and technology adoption in the mining industry right now. So the ATV technology has been around for a very long time. When I was at Core, I did kind of like an analysis and with DGI, and we just kind of wanted to see what the adoption was of this technology. And so we determined that since 2014, with respect to DGI's business, there was an 8-fold increase in the collection of ATV data to the point where it makes up the majority of the business that DGI does currently. And this has largely been driven by improvements in the technology, so better resolution, faster logging speeds, and as a result of faster logging speeds, a reduction in the cost. The cloud, I'm sure you're all familiar with it, but it's basically on-demand availability of compute resources like CPUs and GPUs, data storage and deployment infrastructure. And 5 years ago, I say mining companies were hesitant to adopt cloud technology, but all the cloud providers have kind of addressed a lot of the security concerns that they had. And most major mining companies are on one of the three, so GCP, AWS, or Azure. And lastly, AI is a very popular topic, and we see applications of it all around us. But mining has been slow to adopt it. However, today, I would say that most major mining companies are much more machine learning savvy than they were 5 years ago when I entered the space. And I think that's because they have at least one successful application they can draw on, and they have many more unsuccessful applications. So they understand the value it can bring, how to evaluate the business value of the technology. What are the right applications? What are the wrong applications? So much more willing to adopt a technology solution that uses AI. And so these three things kind of set up what in the AI product space is called the virtuous cycle. And this is where, we might start off with a small data set to create a product. This product attracts some users. Those users create some more data. More data means a better product. A better product means more users mean more data. And you can see how this kicks off. And I think that this is now possible in this space, given these kind of trends that have emerged over the past few years. So with this technology, where are we right now? So we've developed a commercial solution that works with acoustic televiewer breakout data and tries to estimate the stress in deep mines and capture some of the variability. The method is currently outputting the principal stress orientations and providing some constraints on relative magnitude. And the method was adapted from a PhD dissertation by Zajac. And what he was doing was working with breakout data as well, but he was inferring it from a forearm caliper. And he was working on very deep exploration holes in Southern California. So since 2016, we've kind of run pilots of this technology at 10 different mines, mainly in Ontario and Quebec and Utah. So the basic workflow is that we have some volume of rock and we have a bunch of boreholes that are intersecting that volume of rock. We would ideally like this volume of rock to be smaller, and we would like it to be far away from geological structures or mine infrastructure, so that the stress state is not being perturbed. The data is collected on those holes. The analyst will pick the breakouts, and then these breakouts will go into this stress modeling workflow, which will then output the orientations of sigma of the principal stresses and try to provide some confidence intervals as well. So there's a lot of data visualization in this talk, and this is one plot you'll see a lot, so I thought I'd just explain it. This is a polar plot, and so the circumferential dimension is the azimuth. You can see northeast, southwest, and the radial dimension is the tilt of the borehole. So a vertical borehole has a tilt of 0, so that's where you see a little dot in the middle, and a horizontal borehole trending east would be this yellow dot on the right. And so that plot can show the orientation of the borehole. We also want to visualize the dominant orientation of breakout in that borehole. So consider this vertical borehole where you can see these little breakout lobes here. And we have something called the breakout vector, which is just a vector that's pointing in the direction of breakout and is perpendicular to the borehole. And so basically, if we want to show this breakout orientation, it would be this vertical line here. So now we're seeing the trend of the borehole and the trend of the breakout. If I had a deviated borehole, so maybe this borehole has an azimuth of 55 degrees, and you can see the breakout vector on this gray borehole here. So if we project that breakout vector onto the northeast plane and we measure the azimuth, that's what we're plotting here. So here we're measuring showing the orientation of breakout on a deviated borehole. And so the way that this method works, I created a dummy data set here. So imagine we have 6 boreholes across our volume of interest, and the little yellow dots indicate the average trend of those boreholes, and the red line indicates the average trend of breakout on those boreholes. So we have a couple boreholes in the middle. Those are like vertical boreholes, and we have these 2 boreholes out here. Those would be kind of near horizontal boreholes. And what we do is we parameterize a stress tensor with 3 Euler angles and a stress ratio. And if we kind of randomly picked 4 values here, we would get a stress state. So here's our stress state and showing sigma 1, 2, and 3. And on the plot on the left, I'm just showing a black dot. I kind of created a grid of possible borehole orientation. So every black dot is basically an azimuth and a tilt of a possible borehole orientation. And what I did is I said, given those borehole orientations and given this stress state on the right, where would we expect breakout to occur? And that's what the little black line shows. And it's a very simple model. It's assuming the volume of rock is homogeneous, isotropic, and linear elastic, and just looking for the maximum tangential compressive stress around the opening of the borehole. And then projecting it on the northeast plane, that's what the little black line is. And so what the method is doing is basically going to calculate the theoretical breakout orientation at all of our observation points, and then doing like a cost, right? Like an angular residual. How good is a fit is this? And so here we can see that like where the green circles are, that's a relatively good fit. The red circles, it's not as good a fit. So we kind of just iterate through using a global optimization algorithm called basin hopping until we converge on the global minimum. This stress state here produces theoretical breakout orientations at our 6 observation points that best match our observed breakout orientations. And so I have a case study here. So this is a nickel rim depth in Sudbury. Nickel rim south is a mine that's been operating for decades, and it would be kind of over to the right and up. And then what they did is they extended this ramp in red all the way over to the left. And then the proposed site for nickel rim depth, they would sink a shaft down from the end of that and then start to develop that new mine. And that's all in development right now. And we came into this project as they were extending this ramp. The the tubes there, the colored tubes indicate the boreholes, right? We had 12 boreholes. And you can see that some of them are vertical. A lot of the vertical boreholes were commissioned by the geology team. to try to delineate the ore body. And then you see some horizontal boreholes. Those are from the ground control team, and they called those boreholes scout holes. And they kind of would put them out in advance of the tunnel face, do core logging, do ATV logging, and then ESG would put an accelerometer at the end of them. And they're doing this to try to probe this unknown area, because they're kind of venturing to new depths greater than 2 kilometers and a totally different section of the deposit where they've never been before. And so you can see here, most of these boreholes are vertical, and then here are the 3 scout holes. And so 12 boreholes, that was quite a lot of breakouts that got picked from the ATV data. And what this plot is showing is basically a little green dot is showing the orientation of the borehole at a particular breakout pick. And then the red line is showing the breakout azimuth. So that's the trend of the breakout at that pick. So you can see that there's a lot of variability in the breakout orientation. And as well, some of these boreholes change their trend, right? So borehole number 1 here, you can see the azimuth is changing, right? So it's kind of winding towards north, whereas borehole 11 is relatively linear. So the first thing we did is just try to visualize all this data. There's lots going on. And so this is the data from one of the horizontal holes. So we did just basic angular histograms to determine, what is the trend of the breakout. We also looked at the trend of breakout and the trend of the borehole as a function of the distance downhole. So the x-axis here is, on the left-hand side, 0 would be the collar of the borehole, and about 450 meters, that would be the end of the borehole. And this plot on the bottom is a scatter plot, where the y-axis is just the high side angle. So you can see there's a clear symmetric trend here for the breakout. And the radius and the color of these little circles is related to the length of the breakout section. So larger, darker red circles are longer sections. So that darkest point there is about a 7-meter continuous section of breakout that was picked. And so when we calculate the average orientations for each borehole, which is the dark gray line, we are weighting that average by the breakout length. So we can visualize this data. This is for a horizontal scout hole. This is for a vertical hole and another vertical hole. And so there's clearly trends there, but there's quite a lot of variability around those means. So what we did initially was we calculated the weighted average breakout orientation for each borehole. So that kind of simplified the picture, moving into this view on the right-hand side. And that's what we tried to fit our model to. And so we run that kind of optimization process, and what we get is the best matching stress state. So this is our best matching stress state here, sigma 1, 2, and 3. And on the left-hand side is, that grid of possible borehole orientations, and then the red lines are observed orientations from our 12 boreholes. On a per borehole basis, this is kind of a plot to just assess the goodness of fit. The gray histogram is the raw data. The red line is the weighted average that we're trying to fit our model to. And the black line is the best fitting model. So basically the model is trying, or the optimization is trying to minimize the difference between the red line, the black line across the 12 boreholes. The next thing we did is that, as you saw, there's quite a lot of variability in this data. And so we wanted to try to quantify it better, as opposed to just reporting one stress state to the client. So what we did is we ran hundreds of simulations of our stress inversion, and each time we added a bit of angular noise to those weighted averages. So the weighted averages are the red lines, and then the blue lines are those weighted averages plus a bit of random noise, and just ran this over and over and over again to try to map out the object space a bit better. And so when we did this, we saw that sigma 1 was relatively well constrained. It wasn't moving much, and it was always coming out as a horizontal stress. But you can see that sigma 2 and sigma 3 were kind of freely rotating, and either one of them for any particular simulation could have been the vertical stress. So we made a recommendation to the company to log another hole. And so they asked us, where should we drill another hole? So what we did is dove back into the Monte Carlo data and tried to see where there was the most variability in breakout orientations. And the idea here was that, like, if we look at some of these regions over here, like horizontal holes to the northeast, if we had drilled another hole there, we wouldn't expect that observation to help better constrain the model, because even when adding in all of this angular noise, we don't see a lot of variability in that zone. So we did a heat map and we proposed these 3 areas where there was the most observed variability across our simulations. And we said, choose the orientation that kind of aligns best with your drill plan, because they were doing a lot of drilling for ore delineation. And they ended up choosing this one here. So that's the new borehole that they drilled and logged. And that's it there. And there's our new data point, right? So we have this southwest azimuth and a tilt of 48 degrees. So we rerun the optimization. And again, we see something similar. You see sigma 3 has moved closer to vertical. Sigma 1 has not moved. And that's our new borehole. And when we compare the Monte Carlo simulations from our initial 12 boreholes to our second stage, where we added that 13th borehole, where we chose the orientation ourselves, we can see that we've kind of stopped this issue of the rotating stress states. And sigma 2 and sigma 3 are better constrained than they previously were. So the deliverables here were just these principal stress orientations and the stress ratio. So we gave that to the client and we stopped all of our model development. We did this because we wanted to try to do this in isolation and not really understanding what they thought the stress was in their mind, trying to be as unbiased as possible. So once we kind of submitted our final stress state to the client, we then went and did some external validation and some internal validation. So external validation, just looking at some of the world stress map data from the Sudbury Basin. And the internal validation was like looking at microseismic observations, comparing with their existing stress state, discussing with the ground control team about what they thought the stress state was. And then there was another company called Beck Engineering that at the time was doing their own independent assessment of stress at the mine. So we had that as well to compare to. So we went to the world stress map and grabbed the data from the basin. So these green data points, those are all the overcoring measurements from the world stress map. So kind of showing a northeast trend. This magenta data is from a publication that I found from Craig Mine, where they were actually using the acoustic emission Kaiser effect method. So they had a bunch of, I think about 10 tests that they did. The red line over here, that's our stress state for the nickel rim depth project. And then in blue, that's Beck Engineering's stress state for nickel rim south. And interestingly, the kind of old legacy overcoring measurements that were done at nickel rim mine are actually here, about 90 degrees out from both the assessment done by Core and by Beck Engineering. Now, this wasn't what the ground control team thought that the stress state was. They thought it was wrong, but they kind of only had this these legacy overcoring measurements to go off of. But it was inconsistent with the kind of observations they were making at the mine. We also pulled all the microseismic data from ESG and plotted it up. And here you can see the microseismic activity is happening here along the axis, perpendicular to what we said was the maximum horizontal stress of sigma 1, which validates the model in a way. And another interesting thing that came out of this was we were working with a similar data set at the same time, doing the same thing at Onaping Mine, which is just across the Sudbury Basin, also owned by Glencore. And Onaping was doing the same thing, like with these horizontal scout holes and logging the ATV data. And they observed this rock burst. This is an actual image of a rock burst at Onaping. And they thought to go back into the core data, the core photography, and look at what the core looked like in this region. So that's the core. So, some mechanical breaks, natural fractures, no disking, good recovery. Then they asked us to go into the ATV data because actually the ATV data overlapped, like it went right through this volume where the rock burst eventually occurred. And this is what the ATV data looked like. And so this big drop in reflectivity, this big increase in the borehole diameter, that was at the exact point downhole where that rock burst eventually occurred. And interestingly, if you look at the trend of the borehole actually deviated when it was being drilled as it went through this section. And so this observation of this kind of anomalous data in the ATV record is kind of supporting some further work that we're proposing. So what's next? I think the first thing is we need to address the manual processing of this data. It's probably one of the largest barriers to the widespread adoption of ATV data is that, you could imagine like tens of boreholes, thousands of meters of ATV data, thousands of fractures and breakouts. It takes a human analyst a long time to process that data. And so there's a delay between the time that the data is acquired and when the final process results are delivered to the client. But this task is relatively straightforward, right? You're fitting sinusoidal features to fractures and you're drawing boxes around breakouts. And so, just taking technology that is readily deployed in self-driving cars at the moment, or like a Tesla for detection and localization, classification and segmentation, adopting those state-of-the-art technologies and applying them to this problem where we actually have quite a lot of labeled data because this is being done manually at the moment. This would speed up the process, meaning that like minutes after this ATV data was collected, you could have the process results and a stress interpretation available. Secondly, we talked about this anomaly that we saw. And you might think that, well, I have this borehole and I could maybe build a machine learning model. A lot of people have talked about this, where it could be a binary classifier, right? Is this a rock burst area or is it not? And you could imagine dividing up this data and assigning a positive label to these kind of purple area where the rock burst was and a negative label to everywhere else. The problem with this is that rock bursts are very rare events. And rarer still are ATV data that's co-located with a rock burst. There's actually only one example that I know of, and you're looking at it. So this would result in an incredibly imbalanced data set. 99.999% of the ATV data is unassociated with a rock burst. And so I think that we need to flip this around a little bit and approach it more from an anomaly detection point of view, and maybe use like some type of representation learning to learn, embeddings of this high dimensional data space and define like a distribution that is associated with, normal, right? Not rock burst. And then prospectively, as we move forward with this, the mining and new boreholes, we look for data points that fall outside of this tight distribution that we've defined as normal, maybe flag those for the ground control team to go in and further investigate and understand, why it's falling outside of this normal distribution. Another thing we're working on is updating the stress inversion procedure. So, we run it at 10 pilot sites. It did well, but there's clearly room for improvement. As we mentioned, the models only fit to the average of a highly variable signal. The model's limited to isotropic rock, whereas much of the rock that you would encounter in mines across Canada would be heavily anisotropic. The model does not provide usable information about stress magnitude, so you're still going to have to do an overcoring measurement or a mini hydrofrac experiment. And we really don't provide any guidance about planning. So if a company said, I want to do this, how many boreholes, in what orientations, how long should those boreholes be in order to properly constrain the stress model? I think we can make big improvements there. And so we're kind of proposing this new workflow. Parts of this are being worked on in collaboration with John Harrison, who's a professor at U of T, and we have a student named Leo, who's going to be tackling some of these problems. But I think first we're trying to apply Bayesian statistics to better quantify the uncertainty. in these stress states. Try to build out a module for drill plan proposal. So we could say, this is where you should drill your holes. This is how long they should be in order to have the best chance of constraining your model, and also doing it iteratively. So updating the drill plan based on what we observed from previous holes. Try to provide some constraints on stress magnitudes. I mean, I don't think we're going to be able to output stress magnitudes, but perhaps we could provide some upper and lower bounds for some of the components. And then also flagging local deviations. So this is a figure from Fang's thesis, and it's a series of overcoring measurements down the length of a borehole. And you can see that there's a very clear rotation of the stress at this fault. And so, this is a great technique for, identifying faults perhaps that we didn't know were there, or faults that are having an impact on stress, developing algorithms to identify these change points, and then relaying that information to the ground control team, I think would be a useful output for this data. And lastly, getting back to the opportunity, we really want to create an integrated system. So, the moment that this data, ATV data, is collected and ends up in the cloud, it's automatically processed and a preliminary stress model is presented, and then further tuned by an analyst. That would be kind of the desired outcome and what we're, I think, working towards. So this is a bunch of references of different work that I cited during this presentation, and that's it. And I mean, the project's ongoing, and looking for interested students. So if any of this is of interest to you, or you have any ideas, please feel free to drop me a line. Thank you.
Thank you, Dr. Sebastian, for that very excellent talk. So now we'll be taking questions. If anyone has any, feel free to raise your hand or enter it in the chat. We had a question a while ago from Ali. So this is probably, I think, towards the beginning of the presentation. How do you ensure that the ATV is in the center of the hole?
Yeah, great question. So sometimes there are some of the pre-processing steps before any fractures are picked, is that there's a centralization correction that's done, because we generally expect, like in the casing area, that the travel time should be even, right, all the way around. So there is a centralization correction that's done, or calibration, and then also the probe itself has these kind of like springs, basically. So 4 springs at 90 degrees to each other, and those kind of press up against the rock and try to keep it centralized. But sometimes there are issues with centralization, and it can actually be a bit of a challenge when you're interpreting breakouts, because you could have a feature that kind of looks like a breakout, but it's actually just a result of bad centralization. The analysts can pick this up very easily. But this would be, when we're talking about automating the process with computer vision, this would be something that we'd have to address, because we wouldn't want the model to pick those as breakouts.
Thank you. So the second question we have is, has there been any validation for ATV versus axial core, meaning to see drilling-induced fractures and understanding their properties?
So do you mean, I guess what you mean is like mechanical fractures in the core, and using the ATV data to identify those, like mechanical breaks? Is that?
Yeah, I think that's what it is.
Yeah. So yeah, that's a big problem with any core analysis. I saw an interesting study. I don't know where it was, but it was basically like so it was an analysis of RQD, right? And what they did is they measured RQD at different points throughout the core's journey to the core shed. So they took the rock out of the ground, like put it in the core boxes, like in the drill shack, and measured RQD, right? Then the core goes on a truck and is taken to some intermediate storage site. They measured the RQD there. Then on another truck to the core shed, they measured it there. And then at different stages in the core logging process, they measured RQD. And of course, what they found is that the RQD dropped, right? the RQD was highest at the site, at the drill, and then it dropped because of these mechanical breaks. Now, I think that mechanical breaks should be, in most cases, they're fairly easy to identify because, if you open up the core, you usually have a very smooth, like fresh fracture. It doesn't look like it's been there for a long time. But I think it's more a problem with consistency of logging. So yes, I mean, technically, there are no mechanical breaks downhole. So this would be a method to also kind of check your RQD that you're getting in the core shed and making sure that it's not being biased towards the low side because of mechanical breaks. Yeah. I've never seen that being done though.
Oh, thank you for the answer. Got another question from Amir. So for the Monte Carlo simulation, did you use a univariate model or a multivariate? So tuples of sigma 1, 2, and 3?
So basically what it was it's the exact same stress inversion model. And basically the only thing that's done is that every simulation, that average breakout orientation across all the boreholes, we kind of did a random sample. So maybe that's what he means. Like each borehole had its own random sample of noise added to it. And then the inversion was done to produce a stress state and then on to the next simulation. I don't know if that answers the question.
Thank you. So we have a raised hand from Greg. I'm not sure if he wants to
Sure,
unmute.
I can.
Yeah.
Yeah. Hey Seb, thanks for the talk. It was I think I did catch some of this a few years back when you're still at core, and I thought it was really interesting then. But what constitutes a breakout? Is there a criterion for which there's a certain length or a certain depth? And if it's a certain depth, like how do you know that it's just not like a small little chip off the side of the wall versus something that's like a couple centimeters in depth? And then on top of that, how does it relate to the stress inversion when we're dealing with trying to put stress data to a breakout?
Yeah, no, it's a great point. So, when we were working, when we did all of these analysis, we're just taking what the analysts present us with, right? So these are people who are, they're all geotechnical or engineers or geologists. They've been picking breakout for a long time. And it is basically up to them to determine what a breakout is. And I would say that they're probably picking everything, right? So those little chips that you're talking about that are just like, induced by drilling, they're just picking those. So what I think is that part of the variability in the signal is related to the actual variability of stress in the volume. And part of it is related to like operator error, right? And so I think that this is where a better quantification of the uncertainty comes from. I think what we have on our side is a lot of data. We're talking hundreds of thousands of observations per borehole. So you might expect that that kind of error would be kind of drowned out by just working with averages. But I think that there's a lot of room for improvement on this front. And also, maybe on the orientation of the breakout as well, because, we're just fitting this rectangle, but we actually have the full three-dimensional geometry, right, of that breakout sequence. So perhaps we could also do a better job of classifying breakouts by using that depth information more than we currently are. But it's a good point, and then it was always kind of we were aware of it, but we just kind of accepted that that's what the expert analyst was presenting to us.
Okay, thanks. Just quick follow up. The length was used as a weighting parameter. Was the depth as well?
The depth was not. You mean like where it occurred? Usually, what we did is we discarded breakouts from the first few tens of meters from the borehole because we wanted to make sure that these breakouts were not being influenced by the mine geometry itself. So we would kind of filter the data in that way. But no, each breakout was equal and just weighted by its length downhole, but not its position downhole, if that's what you meant.
No. Like the amplitude, like the depth of the breakout itself.
No, but that's so that information is okay. So that's another kind of thing that actually with Professor Harrison and Leo we're working on, is trying to extract more features, because currently our breakout features are the depth downhole, the angle, the length, and the width, right? But there's additional features that we could get from that, right? We could look at the, as you say, the depth into the borehole wall. We could look at the roughness. We could look at the shape, right? Is it a very sharp peak, or is it a kind of a blunted peak? And so that data was never available to us, and it's not something that was extracted from WellCAD. But we now have all the raw data, so we're going to be going in and trying to enrich the feature set in some of these ways that you're talking about.
Cool. Thanks. Looking forward to it.
Cool. Thanks, Greg.
Yeah, thank you for all the questions. I think we've reached the end of this session. If you have any other questions, I guess you could feel free to hang around. But I think, yeah, it was a great presentation. Thank you, Dr. Sebastian, for the presentation again. And I hope to see you guys around for the next presentation.
Yeah, my pleasure.
Thank you.